Hi class and welcome back to the final week of Calculus 3. So today's album recommendation is Modern Country by the artist William Tyler. It is an instrumental album. William Tyler plays guitar and is very plays a lot of complicated plucking guitar, kind of like Spanish classical guitar influenced, and this is his album of his take on modern country music. I would not say it really sounds like country music. It sounds more like, uh, you know, bluegrass or folk music. Not really bluegrass, really some sort of folk tradition, but of very elaborately played guitar. So I find this album very peaceful to listen to. I like listening to it in the morning, sometimes on car trips. It's just around the house. It's pretty great listen. So I recommend it. I want to make some comments because we're approaching the final exam, which will be next week. So the review for the final, I will post a review packet focused entirely on vector calculus, on div, grad, and curl, and all the new fundamental theorems of calculus that we've covered, and doing surface integrals, doing volume integrals, doing line integrals, that sort of thing. This will be out later in the week, and then I will post my solutions to it in video format for Friday's lecture. What I want to say to people who are asking, how do I start studying now? The answer is the final will be cumulative. So, because we're also covering the material from midterms 1, 2, and 3, in addition to everything since midterm 3, you can go back and do the old midterms and the old midterm review to focus in on, to figure out what is worth reviewing. So I've posted midterms 1, 2, and 3 on the course website. And I recommend that, if you look back at your copy of midterm 1, 2, and 3 from Gradescope, you can look over what you got wrong or just attempt doing the midterms again, maybe without the time pressure of taking the exam seated. You'll do better. Maybe you'll realize that things that were confusing before, like cross products, now that we've done them hundreds of times, they're a lot easier. But take a look at it, and you'll start seeing some connections between things we talked about early in the class, like gradients and level curves and things like that, to material that we've been talking about more recently. So I'd recommend starting there, and then I'll post another review for the vector calculus portion of the exam later in the week, along with some details about exactly what to expect from the final exam, sort of. So let's start, as we have for the last couple of classes, by going over our fundamental theorems of calculus, because today we're going to put them in maybe a slightly different context than we did when we presented them, and try to view kind of strategy for how you pick which one to use, what you should be looking for, and how to use these different very powerful theorems. So here's all of them. So as long as you remember that in order to make sense of both sides, you need to have derivatives be continuous and defined, you should be good, right? And so here's all your major theorems, and it's worth knowing their names. So the first one's just the ordinary fundamental theorem of calculus. The second one's the fundamental theorem of calculus for line integrals. But it's also totally okay just to call it the fundamental theorem of calculus. I don't consider that a misuse. These two are Green's theorem This is the divergence theorem. And the last is Stokes' theorem. And it's worth pointing out that there's orientations in all of these that kind of matter. So in the first one, I've denoted it by this arrow telling you you go from A to B, and that determines the order of integration, and if you flip it you get negative of the answer, and that's going to be true for all of these. If you switch orientations, you're going to get negative the answer you should have gotten. So for the line integrals, our paths are parameterized, and the orientation determines which way the parameter goes, from the start to the end, not from the end to the start. And so when you draw this arrow, it's kind of telling you which way dp should be pointing. It should be pointing tangent in that direction. For Green's theorem, we have this two-dimensional region, and the region is oriented in the plane, which means it's oriented x then y positively, which then gives this counterclockwise orientation on the boundary. Another way to think about this is in terms of Stokes' theorem, which we'll come back to when we talk about Stokes' theorem at the end. So the dp orientation here gives this orientation on dr, and you should think that the standard orientation on the xy plane gives the orientation on the area here. But it's less obvious kind of how it factors in on this side, but it does matter on this side totally. So on this side, where it matters is kind of how f, the fact that f, this curl ends up pointing in the positive z direction off of the plane, and so lining up with the positive orientation on r. But we'll talk about that for Stokes' theorem again, so we'll come back. But this side, just dp, the boundary. That's important. So here, dn is always the outward normal, so let's just draw that in a different color. N prime always ends up pointing out, so dn is going to point outward normal to the boundary. So you should always think that if you're walking along the boundary, left is in, right is out, and that's why outward normal makes sense here. But as long as you have this picture in your mind, counterclockwise, outward normal, you have the right orientations. So that's Green's theorem for the divergence form of Green's theorem. Then for the divergence theorem, the right-hand side, you can see the orientation depends on this this n hat. So n hat tells you is out, which is the standard choice, is out the positive orientation or is in the positive orientation on the surface. And so the way this is set up by default is that outwards normal is always the positive orientation, so the same as the Green's divergence theorem form, outward normal agrees. So here, outward normal is our orientation. And for Stokes' theorem, there's more clearly an orientation on both sides. So dp on this side is telling you this direction to move in the boundary. And since the boundary is maybe a little difficult to see in this picture, I drew it out here on the side, but I'm just kind of blowing it out so that you can see it. So dp tells you the orientation here, and n hat tells you an orientation on r. And so as I've drawn it, n hat should be like the outward normal on r, but there's no inside region here. So once I've picked it, though, you should imagine moving, if you move n hat close to the boundary and used right-hand rule. Right-hand rule tells you that you should be rotating. There's local, positive rotation would be locally counterclockwise around the axis n hat. So n hat is up for counterclockwise here. And that tells you that the boundary should be going in this direction, which looks counterclockwise when viewed from above, but again, there's a question of like what is above, what's below, so yeah. What I want to point out is that Green's theorem is really the Stokes theorem, but in 2 dimensions. So in Stokes theorem, this region R can extend into a 3rd dimension, which is why I'm always drawing it kind of like a cap or a mountain. But if R were entirely in the xy plane, you'd end up like a picture up here. And then n hat would be pointing straight up. And so that means n hat would be k hat. It would be the z direction. And you can see that that gives the counterclockwise orientation on the boundary in the plane. So you can just double check that. Let's scroll down and write this down here. So if R is in the xy plane and n hat equals k hat, gives the positive orientation, then ds also is just dA because there's no height to the function. The graph has like height 0 everywhere. So you should think of this whole expression, the curl of f dot n hat ds, is really just double integral over the region R of the curl of f. Well, the curl is always pointing straight up, dot k hat. And so that now gives you scalar curl dA. So that's like the scalar curl of f, just restricted to the plane z equals 0, dA. And that now looks a lot more like, I'm just going to underline this in a different color. No, I'm just going to point it like, this form of Green's theorem. I've got scalar curl. This is just a number because we're in 2 dimensions, dA. And then you can turn it into the form for the boundary, which looks exactly the same. So Green's theorem, Stokes theorem, kind of 2 sides of the same coin. Stokes theorem is strictly better. It's just the improved version that can work freely in 3-dimensional space. And I should point out the boundary of R doesn't have to be in one plane. So I've drawn it kind of wiggly, and my intention there was maybe to say that maybe you're seeing this as like all living in one plane, but you could also see it as a path that's going uphill and like kind of a long wiggle. So this could be like a roller coaster, and then with a cap on top of the roller coaster. So that's the sort of place where you can apply Stokes' theorem. So which theorem should you use? Well, if you have a 2D region, so it's given in the xy plane, you probably want to use Green's theorem. And you could think about that as Stokes' theorem boiled down to a 2D region, but you just probably want to use one of the forms of Green's theorem. But on the other hand, if you are given a 3D region, so it's given in R3 instead of in R2, then you have choices. So option 1 is maybe you're computing flux. And if you're computing flux through a surface, then this is the divergence theorem. On the other hand, you could be computing flow or local circulation on a surface, which is maybe the better way. It's the flow of the curl, but yeah, let's just call it local circulation of the surface. Then this is Stokes' theorem. And so you kind of have these three different opportunities to you. And so a word of warning I want to give is it's easy to ask, like, so how easy can I make my life? So in particular, can I use multiple of these theorems? So if I start with some sort of like 2D integral over R, could I set it up to equal a single integral over the boundary of R and then turn it into some sort of like f of, what have I been writing? F of the end minus f of the start integral. So could I use like fundamental theorem of calculus for line integrals and like some form of Green's theorem to turn every 2D integral down into just evaluation? That would be so great. And so let's fill in from the right to figure out what each of these has to be. So in order to use fundamental theorem of calculus for line integrals, you have to be integrating a gradient field and the flow along it. But then in order to be doing Green's theorem, you have to take the curl of the vector field that you're computing flow of. So over here, we'd have to be computing the scalar curl of the gradient field dA. And so the question is, well, how often do you get this type of integral? Right, so like, how many times have I been giving you some sort of complicated polar integral or something that was really hard to do, but maybe you could have applied Green's theorem, then the fundamental theorem of calculus for line integrals, and reduce it down to a very easy answer? And the answer is never. So let's explore why. Or perhaps the answer is always. And the answer why is because all of these are always equal to 0, and it doesn't matter what you decided to start with. If you've written down these two pairs of equalities, I know that the answer is 0 for all of these cases. So let's first look at this right one. So I don't love that brace. Let's just write it like this. So why is this equal to 0? Okay, so on the left-hand side, we have a gradient field, and we're integrating the flow around a closed loop. Gradient fields are conservative, which means that the integral around a closed loop of a gradient field is always 0. That was one of our definitions for kind of like one of the three related definitions for when a field is gradient, is that its flow along any closed loop is always 0. And then also on the right-hand side, the boundary of R is a closed loop, which means that the end and the start are the same place, which means that f of the end is definitely the same as the value of f at the start, because they're at the same place, and f is some function. And so therefore the difference is equal to 0. So both sides there have to be equal to 0. And this right side actually is also 0. And the reason for that is I'm computing the scalar curl of a gradient field. And gradient fields all have scalar curl equal to 0. In fact, we said that you're a gradient field if and only if your scalar curl equals 0. That was the Clairaut theorem, or the Clairaut test, right? So Clairaut said that some, let's call it G, is equal to the gradient of f if and only if the scalar curl of G is 0. And so, in particular, this scalar curl has to be 0. So you're never going to see me ask you an integral, a double integral over R of nabla across nabla f, because that's just 0. It's always 0. I'm integrating 0 over a region, so it'll be 0. Then when I move over to the right, I'm integrating something that's potentially non-zero, but has to add up to 0 because it's a gradient field. And then, so that's this middle one. And over here, I'm taking two different values, which, you know, the function can be interesting, but the values at both of these places have to be equal to each other. So that has to be equal to 0. So all of this is just 0. So you can't really daisy chain together the fundamental theorems of calculus. You can only kind of go back and forth over one theorem. So at the end of last lecture, I kind of used Stokes' theorem twice to go from a region to a boundary and then from a boundary to a different region. That's doable, but you can't keep going down in dimensions, in repeated dimensions. So, word of warning. Yeah, so you can't daisy chain together fundamental theorems of calculus to keep reducing dimensions. You only get one dimension that you get to reduce it by. And that's the only chance to make things easier, and that's it. Or one chance to go up and make things easier. So that's it. You get one step. So let's do the same thing up a dimension. And we expect to, again, get 0, but let's see what's happening. So let's start with the divergence theorem. So let's say I have some triple integral over some region, but I want to apply a divergence theorem that then I can apply Stokes' theorem to. So what that's going to mean is I have to start with a divergence of something I can take Stokes' theorem of, which means that it has to be a curl, so I'm computing circulation, dv. And now by divergence theorem, that looks like the double integral over the boundary, and this is now over a closed curve, or a closed boundary, of the curl of f and I'm computing the local circulation. And now I can try applying Stokes' theorem. So here's the divergence theorem. And here's Stokes. And Stokes' theorem says, okay, what you should do is you've got a surface, so now you compute the integral over its boundary. So I'm going to write that as boundary R, because I started with boundary R. And I just compute the flow, f dot dp. Okay, now it turns out all of these are also equal to 0. So y is easiest to see from the right. So let's fill it in. So boundary R is closed. So it's a closed surface, is a closed surface. So it has no boundary. So closed surfaces are defined to be those that are without boundary. So when so we said we can basically apply Stokes' theorem to things that look like, some sort of cap. So if you have this has a boundary, right, that bottom. But divergence theorem we've been mostly applying to surfaces that had, that were maybe solid. So if you fill this surface in and you take its boundary, so if this is R, then boundary R looks like both the top and the bottom. So it's that plus the little disk on the bottom. So I'm thinking of it like a upper half sphere. And that itself has no boundary because you have kind of like the two halves of the circle that are canceling each other on each of these pieces. Put another way, so if you start with a sphere, maybe this is the easiest example to see. So if you start with a solid ball, when you take boundary, you end up with a sphere. And then when you take another boundary, you end up with nothing, because there's just nothing there. The way you should think about this upper half of a sphere, let's just draw it better. So when you take boundary on it, you end up with two halves, one which is the upper half of the sphere, so I'm going to draw that like this. So the upper half of the sphere. And remember that things are getting the outward orientation, so that's oriented like that. But you also get this lower disk. And that disk is also given the outward orientation, so that's the down orientation. Now when you take boundaries on both of these, on the top you end up with a circle. And that circle, if you wiggle that yellow arrow over towards the edge, is oriented in that direction. So it's oriented going around. And down here, the disk also has a boundary that's a circle, but it's oriented from below. So that orientation now goes clockwise from above, or counterclockwise from below. And so these guys cancel. And this is always going to happen, that if you have some closed surface and all your edges meet together, if you picked the outward normal orientation on each of the faces, then when you take boundary a second time, all of the little boundary components cancel each other. You can check this with a square or with a cube. You can check this with, you can also check this with a square. You can check it with a tetrahedron. You can check it with anything you draw. So as long as you're careful with your orientations, this is guaranteed to work. And it also trivially works when there's just things like spheres where there's no boundary. So all of that was a really long-winded way of saying the double boundary of R is nothing. So this integral is 0 because I'm integrating over no points. I'm just adding up nothing, the flow along nothing. So that has to be 0. Which then means that the local circulation of, well, F here was anything, right? So any field F over a closed surface is 0. And that's a new piece of data that we didn't know before, but is kind of implied by Stokes' theorem. It's implied by Stokes' theorem, right? And now, on the left-hand side, this also has to equal 0, but the new piece of data it tells us is that really, this doesn't have to be 0 for any reason at all, except that this, the divergence of a curl, is always equal to 0. In fact, you can check by taking partial derivatives. So compute this formula for just f equal to mno, like whatever you want to write it is, let's say mnp, that this formula, you compute the curl first, and then you compute the divergence of the curl. Things always cancel out and give you 0. So and that is a new piece of data. In fact, let's check this. So I quickly computed the curl, right? So the curl of f, if f is mnp, is py minus nz, mz minus px, and nx minus my. And so then the divergence of the curl is just equal to, take the first one with respect to z, so that's py x, with respect to x, minus nzx plus mzx minus pxx, y. mzy minus pxy plus nxz minus myz. And then, as long as we know that these second partial derivatives are continuous, which they have to be for all of these theorems above, then we know the mixed partials are equal, and you get to cancel those two, and those two, and those two, so you just always get 0. Let's put this in context. So recall that C infinity from x to y means infinitely differentiable functions from x to y. And so we've got this kind of like R2 picture, which looks something like this. So if I have a C infinity function from R2 to R, so think of that as being the function f, then I can take the gradient of f, and I produce a vector field. So a vector field is now a C infinity function from R2 to R2. So we talked about this back when we talked about gradients. And what we can do with vector fields is compute their scalar curl. So I'm going to denote it like that, but this takes a gradient vector field to the scalar curl, which is always 0 for gradients. C infinity. And scalar curl is now scalar valued, so this is from R2 to R. And so we have this special case where if you take something 2 steps to the right, it becomes 0. And in fact, we know that this special property that if under this map you are a vector field which goes to 0, you have to actually be a gradient vector field. So in fact, these are the only things going to 0 under the map, which is pretty powerful. We now also have context for this picture in R3. So let's give it. So in R3, we can start with a function. So let's call that function f. And we can do the same thing. We can take its gradient. And the gradient is now a vector field. So that's a C infinity function from R3 to R3. And we know that if you compute the curl of the gradient, you're going to get 0. So I'll take curl here. Now curl, though, is produces vector fields, right? So this is, maybe I should write this 0 with a vector on top. This is a C infinity function from R R3 to R3. But we also can go one further step here. So we can also take divergence. So I just want to put this here as grad, here's curl, and here's divergence, which produces scalar functions from R3 to R. And now it's not interesting to start with 0 and compute its divergence. It's still definitely 0, but I could have come back here and picked a different vector field at step 2. And if I compute its curl, and then its divergence, we end up with this divergence of curl. And we just checked that this is always 0. And in fact, the interesting thing is this also is has the property that the only vector fields whose divergence is 0 are the ones where, in this step, which are curls. So another way to put that is, so just for R3, if the curl of f is 0, then it has to be that f is gradient. So if the gradient of some function, let's say p for potential. But also, it's if the divergence of f is 0, then it has to be that f is secretly the curl of a different vector field G. So, and we don't have a name for this, like circulation vector fields or something like that. But another way to, and this is a special property of R3, so don't sort of generalizes, sort of doesn't. But the thing to talk about here is that we have two of these two-step 0 things. So this one's easy to remember. If you do curl of curl of grad, it's always 0. And that's the same here. Curl of grad is 0. But we also know divergence of curl is 0. And so we have these two different two-step processes which always give us 0. Okay, example 1. Let f be 3y minus x cubed. I'm considering f as a function of x and y. Compute or explain why each of these things is nonsense. Pause here, answer the question. Okay, so I get that the gradient, that looks like, that's a reasonable thing. That's the derivative of this function. That should be minus 3x squared, comma 3. I only have x and y derivatives, and the gradient should be a vector field on R2. The curl is meaningless. The curl is the thing we only take of vector fields. So this is nothing. Curl only eats or consumes or applies to vector fields. Likewise, divergence only eats vector fields. And in case that explanation feels unsettling, like, remember, this is just a fancy version of the question, can I take a cross product of a vector with a scalar? F is a scalar value, scalar valued function, right? So if you plug in x and y, you just get a number. So, and nabla is a vector. It's ddx, comma ddy. I can't cross a vector with a number. I also can't take a dot product of a vector and a scalar. I can do scalar multiplication, which is what the first one is. This is cross product, and this is dot product. So notice back at the very beginning of the course, when we talked about scalar multiplication, then the dot product, then the cross product, we were actually talking about gradient, and then divergence, and then curl, even though we were only doing it for vectors, not for vector-valued functions and vector fields yet. Now, the last two things are a little bit more complicated because the gradient of f is actually a vector field, so I can compute the curl of the vector field. But that's always 0 because this is a gradient vector field. On the other hand, the divergence of the gradient is a meaningful thing. It's not necessarily equal to 0, and I can compute it. So I just go back up to this top line, and I take the divergence. So divergence is ddx of the first slot, so that's minus 6x plus ddy of the second slot, which is 0. Example 2, same question, but I am changing my function to be on R3 and to be 3yz minus x cubed. Go. Okay, I got minus 3x squared, comma, 3z, comma, 3y. Because gradient needs to be a vector field on R3. Now, both of these are both still nonsense because it is crazy to compute cross products or dot products with scalars, and f is still scalar valued. But both of the last ones have meaning. The first is absolutely equal to 0 because I took a gradient vector field, and curl of gradient is always 0. And the last one is not necessarily equal to 0, and I can compute it. It's minus 6x plus 0, which is d3z dy, plus 0 from the last component. So that maybe gives some sense of how I can quickly, by remembering curl of grad is 0, compute some of these values. You should also think about this as type checking. So if you come from a computer science background, people call it type checking. You can only evaluate the right types in the right types of functions. So cross product only eats vectors, and that's why this is nonsense. In science classes, this is sometimes called dimensional analysis, right? You have to check that your answer even makes any sense before knowing if you have the right form. Tells you whether you have the right formula or not. So, okay, let's make the problem a little bit different. Now f is of a function on R2 that is valued in R2, and its output is x squared minus y, comma 3y minus x cubed. Compute which is nonsense and which are computable. So for me, the first is nonsense. I can't even spell it. This is nonsense because it would be scalar multiplication of nabla with f, but f is a vector. So this is like two vectors trying to be scalar multiplied. That doesn't make sense. But I can compute curl, and I can also compute divergence. So let me compute each of those. So curl, this is scalar curl because I'm in 2 dimensions. So I just remember that it's dx of the last component and d minus dy of the first component. So that's minus 3x squared minus derivative of minus y, so that's minus 1. So this is just 1 minus 3x squared would be my answer. My divergence, that's like with like, so that's 2x plus 3. Now, the last two, that's a nonsense term, so I can't then take a cross product or then take a dot product. These both are nonsense as well, because if one of the components in it is nonsense, the whole thing's nonsense. Okay, and finally, we're going to go back up to 3 dimensions, and here's our new vector field, compute, explain why each is nonsense. So the gradient, again, this is nonsense, and so are the last two. And the issue is this gradient of f term makes no sense, but I can definitely compute the curl. And because I've got x's, y's, and z's, let's compute it as a determinant, just so I make sure I get all my terms right. ijk, d dx, d dy, d dz, z, x plus y plus z, y plus 2z. So my output is 1 minus 1, and then in the j component, I've got this extra negative, and its ddx is 0 minus 1, and then in the k component, I've got 1 minus 0. So my final answer is 0, 1, 1 is my curl. It's a constant curl. And my divergence, that's like with like, so it's much easier to compute. 0 plus 1 plus 2. So I have divergence 3. Okay, let's now use our fundamental theorems of calculus to actually compute some integrals. So here are my integrals. I've got C is the circle with radius 3, center of the origin, and H is the top half of the circle with y greater than or equal to 0. And I want you to compute each of these. Definitely start with A and B first, and then try to do C and D, and then check back in. So for A and B, I'm going to set up some terminology. So I'm going to let, so C is this circle, and I'm going to orient it counterclockwise. H is this top half of the circle, and it's also oriented counterclockwise. C and H's orientation are not specified in the problem because they don't have to be. They're just regions of the plane when you set up an integral like this. But when you pass to the line integral, you have to use the standard orientation of the plane and the standard counterclockwise orientation of curves in order to have the two sides equal to each other. So in order to make sure that you're, in fact, computing the right thing, not negative the right thing. So just always use the standard orientations and you'll be happy. And I'm also going to define the interior of this circle to be D for disk, again with a standard positive orientation. So for the first problem, I'm going to let F be my vector field 2x minus 2x. And then I'm going to compute the curl of F, scalar curl because I'm in 2 dimensions, so it's minus 2 minus 0. And then by Green's theorem, this is the double integral over the disk. Disk has radius 3 of minus 2 dA, which means that my answer is minus 2 times pi r, which is 3 squared. And I'm done. For problem 2, I'm going to define g to be 1 plus 2y, comma 2x minus 2y. And then I compute the curl of g to be 2 minus 2. And so that's 2 from the 2x and minus 2 from the plus 2y in the first coordinate, which is 0. So this actually has curl 0, which means that G is a gradient vector field. And so by Green's theorem, this is definitely equal to the double integral of 0 over the disk, dA, which is 0. But you could also think of this as just it's 0 because G is gradient or conservative. And C is a closed curve. Okay, now we're going to do the H thing. So if you were confused by A and B, maybe now my solutions give you some hints for how to then attack H for C and D. So maybe pause here and try them. My solutions, though, because I know G is gradient for this first one, is maybe I could use the path independence of the gradient vector field. And so what I'm going to do is, rather than doing H, I'm going to do, let's just call this P for path, right, in the plane. And remember, I'm in the xy plane, so let's draw my axes. Here's plus 3, here's minus 3, y, x. So by path independence, this is the same, the integral over h is the same as the integral over p. Of the same thing, of g dot dp, which is going to be so I could try to compute, I could do this in two different ways. So one is view this as just I'm integrating from along p, from plus 3 to minus 3, but y is always 0. So, yeah. So use the fact that y is 0 on p to then get that this is the same as evaluating from, I guess, passing to a parameterization of p from x equals plus 3 to x equals minus 3. And so I'm now just walking along p, but I'm computing g dot dp, and g of p is 1 plus 0 dx plus, and then this is 2x minus 0 times 0. And that's because there's the dp gets replaced by p prime dot dt, or in this case, t is x, basically. And p prime has no y component. So maybe the better thing to say here is that if p parameterizes p, then d p d, I'm going to use normal d's, not partials, dp dy is 0. And so that's why there's this 0 here. Which means I'm really just integrating 1 dx from plus 3 to minus 3, which is minus 3 minus plus 3, which is minus 6. The other thing we could have done, and I'm going to take over a little bit of space here, is I could have picked a function for g to be the gradient of. And so you could, by trial and error, pick some antiderivatives and then evaluate at the start and stop. So what kind of works? So I'm going to phrase this way, say, or notice that g is the gradient of, and what does that have to be the gradient of? D dx has to be 1 plus 2y, so it kind of looks like it's maybe x plus 2yx. And then I'm going to just check my other partial derivative. So if I take the derivative with respect to y of this, I get the first x vanishes. The second one gives me 2x, and then I need a minus 2y. So that needs to be coming from a minus y squared. And minus y squared gives me minus 2y, and I've double checked both of them. This works. And so you can also check that minus 6 is the same as evaluating x plus 2yx minus y squared we started at the point 3 comma 0, and we stopped at the point minus 3 comma 0. And so if you plug in 0 for y, all those terms vanish except for the x term, the first one, and then it becomes this minus 3 minus plus 3 that we had above. So you should view this as I passed a parameterization, and you should view this as I picked a function and did fundamental theorem of line integrals. Either works. For the last problem, we actually have only that first option, basically, but we also know that the function's not path independent. So we're going to integrate along p instead of h to make our life easier, but it's just going to change the problem a little bit. So let's spell out this a little bit more carefully. So what I'm going to do is use Green's theorem. And so Green's theorem will tell me that, in short, the integral over this solid upper half disk is equal to integral of the curl over that disk is equal to the integral over h plus the integral over minus p. So I'm going to do p backwards. And so that looks now like the integral over this path plus then do the integral over this path, right? You can see, trying to draw how those connect up. So let's just be really explicit about this. Really what it says is that the double integral over, and I'm going to define that upper half disk. So let's give a name to this. Let's just call this E for Ernie. So the integral over E of the curl of f dA is the same by Green's theorem as the integral over the boundary of E of f dot dp. And the boundary is split up into those two components. So it's first do the integral over h, and then do the integral over p, over minus p. And minus p just means do p in the opposite direction. So what this means is the thing we want, integral over h of f dot dp, we need to compute this as the difference of this double integral over e of the curl. Oh, well, we computed the curl. The curl was minus 2. Okay, so minus, okay, let's try that again. Minus 2 dA of e. So that's that, minus the integral over p going backwards of f dot dp. Okay, and let's just compute this second thing. So let's parameterize p going backwards. So parameterize minus p. And the way I'm going to do that is I'm going to let p of t be t comma 0, because p is entirely along the x-axis. and t is going to go between minus 3 and plus 3, and that parameterizes the curve. If you wanted to parameterize p going forwards, you would start at plus 3 and go to minus 3 like we did up in this integral. But it's a little confusing, so I'm parameterizing going backwards because then the t's go in the positive direction. So, and what does our integral become? So I have forgotten what f was again. Oh, it's 2x. Yeah. Cool. So what I want to compute, f over minus p dp, which is definitely the same as the integral over minus p over p. Let's put it this way. The integral over p of 2x dx minus 2x dy. I put the negative in front because I'm going to get negative of the answer of the integral, and unless you're in vector form for the integral, it's kind of weird to write minus p underneath, but it's just fine. So this is an aside. But the thing I actually want to do is parameterize it, so I'm going to pass to my parameter t. Goes from minus 3 to plus 3. F of p of t becomes, recall f was 2x minus 2x. So f of p of t is 2t 0 dot dp, which is p prime. P prime is 1, 0 dt. And so it's just this right here. That's f of p of t. And this is p prime of t dt. Okay? Those are dotting together. And this means my answer is the integral from minus 3 to plus 3 of 2t dt, which is just t squared from minus 3 to plus 3. At both of those things, it is equal to, it's squaring, so on both of these, it's 9, 3 squared, so this is just 0. Which means that my final answer is kind of magically that all of this equals minus 2 times the area of E. E is half the area of the sphere, so this is minus 2 times a half times pi 3 squared, which means I get minus 9 pi as my answer. I do want to point out you could also parameterize h directly using polar coordinates. Like sine, h can be parameterized as 3 cosine t, comma 3 sine t, and then you can turn this into a polar integral. I think that's harder, and this was really easy, so this is preferred. Okay, I know this lecture is going long, but Wednesdays is going to go short, so this is also sort of part of the review, so I apologize, but let's talk about the, let's go up into 3 dimensions and try to do our divergence and Stokes theorem type problems. So B is now a sphere of radius 3 centered at the origin, H is the top half of B, and F is this vector field that we've actually seen before. For each of these integrals, compute them if they're very easy, or set them up if they're somewhat tedious, and make reference to what theorems you're using. Okay. My first step in this problem is, because I see curls, and maybe I'm thinking about using divergence or Stokes theorem, is I take the curl and the divergence of f in order to know what's potentially an easier replacement for f to use. So compute the curl and divergence of f. Well, we did those a couple slides ago, so the curl was 0, 1, 1, and the divergence is 3. So there's there's what my vector fields look like. So a couple of these are already definitely easy. The easiest is the last one. This is 0 because I'm computing circulation along a closed vector field, or a closed surface, B. So the sphere is our canonical example of a closed surface, and we said earlier that the curl along that is 0 by either Stokes' theorem, by doing another boundary of the boundary of B is empty, or by applying divergence theorem and getting that this is the triple integral over the inside solid ball, like the interior of B, of the divergence of the curl, and that's 0 dV. So either way, it's definitely 0. The other one that I think is going to be easy is C, because I can also use the divergence theorem to pass to the solid ball with radius 3 of the divergence of F dV. And so, right, because this wasn't a circulation, it's just the flux of F through the surface, so I can use divergence theorem. And divergence theorem now tells me this is 3 times the volume of the ball, which is 3 times pi, it's 4/3 pi r cubed, so 3 cubed. That's my answer. And let's see, which other ones are easy? The first one I think is easy, and for that I need a little picture. So here's my picture of H. And I'm going to use, so the boundary of H is this circle. And it's a circle in the xy plane of radius 3. And I'm going to let D be the interior of that disk. So I'm going to let so I'm going to fill in that disk and call that D for this disk in the xy plane, and this is the boundary of D as well. So boundary of H is equal to the boundary of D. So what I can do is use Stokes' theorem. So I know the curl is pretty easy, but what that means is this is the same as the circulation. So computing the circulation of F along H is the same as computing the flow of F along the boundary of H, which is the same as the boundary of D. So this is Stokes. And then I can apply Stokes again to go back to the boundary of this disk, or to go back to the disk, the interior of this disk. And I'm now computing circulation. And I always think of it as Stokes' theorem, not Green's theorem, but you could also think of this as Green's theorem. So n hat ds is much easier now because we're in the plane. And so n hat in particular is just 0, 0, 1. So n hat dot my curl, because my curl is also really easy, is now just 1. So I'm computing 1 times the integral of the surface area of D, but that's just the same as the area of D. So this is pi r squared. So that's very easy. And so I think the last one that looks challenging to set up is this middle one. And so because I'm computing flux of F through the surface, I'm going to use divergence theorem. And what I'll do is I'll write this. So if I write, if I do my math correctly, what I have is that let's define E to be the solid upper ball. So that looks like this, and it's shaded because it's filled. Then the boundary of E looks like H, because it's outward normal, so up, plus minus D, so H minus D. And so if I do the integral of H plus the integral, or minus the integral of D of F dot n hat ds, that should be equal to the triple integral by divergence theorem of the divergence of f dv over E, which is not that bad. And so what I would do is grab, so because I want to solve for this part is easy. That's going to be 3 times 1/2 times pi times 4/3 3 cubed. And I'm just seeing that as volume of the sphere times 1/2 times 3, which is coming from my gradient, or my divergence. And the other component that I need to compute is this, which I could add over to the other side of the equation. And this doesn't look that bad because f, when I parameterize D, my z component is 0. So z equals 0 in D. And so I think this looks like the integral when I add it to this side. So let's just write it as the integral of D of f dot n hat ds. It looks to me like, oh, well, n hat is the is just k again, and ds computes area. So now I'm just getting the z component of f, but z equals 0, so it's just y times 1. So this looks like the double integral over the disk d of y dA. And, that's not that hard to compute. In fact, you can see that y is symmetric. There's half the disk square y is positive and half where y is negative. And so this is actually going to give you 0, kind of for special reasons about this choice of vector field, not just because of some div grad curl type argument. So yeah, so I guess I came to the conclusion that they're all pretty easy. Yeah. See you all on Wednesday. I hope you have a good time studying. Bye.